Ready? I want to go do group 2 first as group 17. Same thing, I want to talk about the topics that are the things they like to test for group 2. Okay? So first thing we need to take note is again the physical properties or the physical trends for your this group 2. You are expected in syllabus to know again there are the 3 that is always involved with the same explanation. What do I mean? First physical trend is anything involving this formula here. ENC, your this nuclear charge over your screening effect. Okay, so we learned that there are 3 physical trends is using this formula to explain, right? So do you know what are the 3? First one is number of protons. Huh? What are you talking about? I mean, no. The trends. First one is? So your first ionization energy. Okay, you use this formula. Second one is, as you go down the group, you also use your electronegativity. We use this formula to explain the trends, alright? That one not really this, but it's actually got to do with your atomic or ionic radius. But I say already, atomic ionic radius, don't really need to use this formula. We just say down the group, number of quantum shells increase. So your this electron cloud size increase, that's why atomic and ionic radii increase. But the rest, you still use this. Nuclear charge, you say increase because increasing number of protons. Screening effect increase significantly because of increasing number of quantum shells, and this increase, you always tell me, will outweigh the increase in nuclear charge. So that's why my ENC will actually decrease. Grace, can you help me close the door because you never close properly? If not, my whole thing will be... Okay, but anyway, continue on. So what else we also use for your this physical trends that we need to take note of, which is your melting point and your E0 cell. So we learn again your melting point. So whenever you want to explain, because we already learned now that first ionization energy will actually decrease, electronegativity decrease, atomic radii and ionic radii will increase. But if I ask you for melting point, Vivian, can you tell me what happens to melting point as you go down the group 2? Wrong. It will actually decrease. Grace, what's the standard explanation to explain why it actually decrease? Remember our melting point or boiling point is always trying to overcome your this electrostatic force of attraction or your metallic bonds. So why? Radii, or which radii? You see atomic. Is it ionic or atomic? Ionic. So ionic radius increase or radii increase. So the C will, so that's why electro becomes, yes, okay, so standard answer is got to do with your ionic radii will increase. So we know that again the electrostatic force of attraction between the positively charged nucleus and the C of delocalized electrons will increase. So that's why your metallic bonds will decrease, lesser energy needed to overcome, melting point will always decrease. Does this also apply for group 1, Vivian? How about your this as long as any other metals? Yes, so in other words, melting point always look at 2 things. Number 1, you always look at your this strength of your this bonds, which is dependent on what? Your ionic radius. This is always what you're looking for. And then you are looking at your this again strength of metallic bonds. Please know metallic bonds is always between your positively charged nucleus and a sea of delocalized electrons. The last trend we need to take note for the physical trends is again your this E0 value. So your E0 value, if I were to write explicitly, is your metal becoming your this metal in the reduction value. So what happens to this? Is it going to be more positive or more negative, Vivian? So again, no. Because you think about this, your group 2, right, you're trying to lose electrons, right? You look at your first IE, you can use logic, first IE decrease, right? Lose electrons much more readily, right? More likely to be reduced or oxidized if you lose electrons more readily. So you're more likely oxidized, what happens to your E naught? Reduction. So it's always going to be more negative. Understand? This is how you see the logic. It's related to your first IE. Now the next thing we need to take note is your chemical trends or your chemical reactions here. For your chemical for group 2, you are expected to learn again these 3 things. What are the 3 things you're expected to learn? Number 1, we are always looking out for thermal decomposition. But I already said already, thermal decomposition is always got to do with what? Again, your size. As we go down, what happens to thermal decomposition, Grace? Is it going to increase or decrease? So again, it is going to be more difficult or less difficult? That's the question. What is it? Is it more difficult or less difficult? So it's going to be more difficult as you actually decompose, okay, down the group of group 2. But we always have the standard template, right? Let's see whether you recall the standard template. There's always one way to explain. So first thing, how do we actually explain, Grace? Try. For example, if I ask you to just compare between BE, okay, carbonate, as well as the other one is calcium carbonate. Which one is more easily decomposed? Calcium, right? Standard answer. So again, always tell me which one. Again, always compare the. So you always say the calcium 2 plus has a. So, and therefore. Yeah, so you always tell me standard template, higher charge density due to, okay, again, higher charge density, lower charge density due to, again, same thing, due to this higher ionic radius and same charge. After which, what do you actually use this to explain there? So again, we always say polarizing power is going to be lower. If polarizing power is lower, the extent of to distort. Okay, the electron cloud of, again, tell me what is the N ion. So in this case, the N ion is CO32 minus, okay? Is to a greater extent, or you can say it's actually lower in this case. Okay, then after which, what happens? It will weaken whatever bond to a lower extent in this case, because you know that you are actually breaking down a CO bond, so you must specify to a lower extent. That's why you will say more difficult to decompose. Standard template, if you want to write BE, you just change accordingly. But this is always the template we have, right? So let's try. This time, if I ask you to compare, we're going to change this up. Copper to carbonate and this. Because we know, by right, when metal carbonates decompose, we have 2 formulas we are expected to learn in syllabus. Decomposition of metal carbonates to give me what, Grace? And next one, the other decomposition we need to take note of is metal nitrate, right? So Vivian, what is it when metal nitrate is decomposed? Metal oxide. NO2 gas, by the way, is what color? Brown. And you will have half moles of O2 in the event if you are just considering your group 2. Okay? So, again, let's say I ask you to compare between copper 2 nitrate as well as this calcium nitrate. Vivian, which one is more readily decomposed? Because they are neither from the same group, right? Neither of them belong to the same group. What? You need to look at your data booklet here. Even I also need to look at data booklet because they belong to the same period. So it's what? Bracket. So it's what? Remember what we always comparing? I say already. Compare what? So you're comparing ionic size. Which one actually has a larger ionic size? So if calcium has a larger ionic size from your data booklet, what must you do? Always have to quote data, right? So calcium is 2 plus or calcium atomic size, which one? Is it the ionic size you compare or the atomic size you compare? So Ca2 plus is what size? And then how about the copper 2 plus? So which one is actually larger? So again, calcium will therefore have a lower charge density due to larger ionic size, same charge. And then polarizing power is lower. Extend to distort the electron cloud of this time. NO3 minus N ion is lower. What bonds are you weakening to the lower extent? NO. You must specify, and that's why it is actually more difficult to decompose. I'm trying to showcase because sometimes they will not just go through group 2, they will ask you to compare other metals. Please know how to compare as well. I can even write Fe2 plus and then you must know which one is more likely to actually be decomposed. Clear? So they always like to test things, right? Not just for trends, metals is related to group 2 trends. Okay? Next one you also expected to learn in syllabus is the, again, amphoteric nature of a particular group 2 metal. What is that particular group 2 metal, Grace? Group 2. Group 2. Beryllium. Understand? So you are expected in syllabus to know about beryllium. Okay, so these are the 2 things. What about beryllium? You are expected to know beryllium, how it behaves. This one, why is it amphoteric? Same with your beryllium hydroxide. They both are amphoteric in nature. So let's try. Let's say if I want to consider both of them as a base, which is actually very simple. If beryllium is behaving like a base, I'm reacting with, let's say, okay, an acid. Products formed, you all should know already, is your beryllium salt as well as H2O, right? Same thing with your beryllium hydroxide. Beryllium hydroxide, we learned is that it's reacting as a base. You will also still form beryllium and H2O. So this time all I need to do is actually what? Balance. This is the balance equation. But, Grace, can you now tell me what will be the equation if I want you to tell me how beryllium oxide and beryllium hydroxide behaves as an acid? So let's start out with beryllium oxide first. You behave as an acid, you react with an alkaline. What will be the product? Because you learn magnesium, you learn aluminium. Remember aluminium? Is it similar? Yes, right? Sorry? You will always form the complex. Do you remember aluminium? I'm going to show you. Let's say I have an aluminium oxide. Do you recall? For what? Plus what? Because of the acid, you must be a proton donor, right? But don't have protons, right? So what must you need to do? Yeah, hydrolyze certain water first so you can release, okay, and behave as a proton. Then what was the product form? LaOH4 and then minus, right? Agree? This one is 2, this one is 3, right? So I can actually balance this, right? Or will it be similar for beryllium oxide? Yes. As an acid, you're supposed to be a proton donor, but you don't have. So you need to hydrolyze with water. So you have to hydrolyze in water first. What do you think will be the complex form? OH for 2 minus. Do you understand? So do you see it's similar? Okay, so it's going to be the similar pattern all the time. So if I want to ask you to change it up, because I say this is also amphoteric, right? So it can behave as an acid. Do you need to add water this time? No need. You have protons to donate. Agree? So what happens? You form BE. Will you form the same thing? Yeah. Yes. 2 minus. You just need a balance. So this is a balance equation. Understand? Okay. So you are expected to think are amphoteric nature. How does BeO as well as Be hydroxide behaves as a amphoteric oxide, or why are they amphoteric in nature? Second thing is that you need to learn how to explain. So what's the standard explanation? Because it's the same exact explanation why aluminium can have amphoteric in nature. Remember, what is the character that gives the acidic property? And then what is the character that gives the alkaline property? Okay, so why? So let's try first. Be. Keeping in mind Be is Be2 plus. So what about how come can have acidic and covalent property within the BeO or within the Be hydroxide? Yes. Sorry? Yes. High charge density. So you are able to, very similarly, because you want to have covalent nature, that means you want to have overlap of orbitals, right? Yeah, let's see whether you recall. To explain, there is always 2 parts to explaining. In this case, you can also put it for your this aluminium. So Be has what? High charge density. So when you have high charge density means what? You can distort or polarize. Okay? The anionic cloud. Alright? So, to exhibit what? What's the keyword? Over. So there's causing, okay? Causing overlap of orbitals. So when you cause overlap of orbitals, again, you have resulting in what? Covalent character. So again, I want to see overlapping of orbitals because you distort or polarize the anionic cloud size. So same thing, how you want to explain acidic character is due to covalent nature of bonding. And then you will say the basic character is due to ionic nature of bonding. Have to mention still basic character or property due to ionic nature of bonding. So always learn the standard answer. For group 2, group 17, they always have standard way of writing, so never lose marks. These are only things they like to test about group 2. Yeah. Next one, I want to do group 17. Can I erase, Vivian? Okay. Same thing for group 17. What are the type of questions they typically like to test? Same thing, physical trends is the first one. For physical trends, I repeat again, there are actually 3 of your this physical trends, so you will use this particular formula, E NC proportional to nuclear charge over my screening effect, which is the 3 trends. What are they, Grace? Name me one. No, I mean the trends is what? Huh? Your head, this is group 17 eh? Electron affinity. What happens to electron affinity? What happens to electron affinity? So again, we have here, so you know this one decrease, right? So electron affinity is what? More exo or more endo? That's the question. More exo or less exo? So again, always tell yourself is less exothermic. Do you know why less exothermic? Let me explain. First one, you should know already, your ENC decrease. So it means that outermost electron less strongly attracted a nucleus, right? Agree? Do you think that it's easier to gain, the willingness to gain an electron actually increase? No, right? Agree? It decreases, right? So in other words, isn't that to gain an electron will be less and less exothermic down the group? Okay, so take note. Next one, another one that we need to take note of is what is the abnormality. So is there any anomalous things? Please take note for this. The abnormality is what? Fluorine. Fluorine, right, is actually going to be even less exo than this chlorine. Do you know why, Grace? It's very ionic, atomic in this case, because you're trying to gain an electron, right? So initially it's the atomic size. I repeat, I draw a simple one. Atomic size. Because you have yet to gain. If you say ionic, then why is it going to gain? Agree? So what happens to your atomic size? It actually is larger, right? In chlorine, but fluorine is so small. So having such a small atomic size, what happens here? It means that, again, your repulsion is going to be greater if you try to receive an electron, right? Agree? So, as such, what must you mention? All you need to tell me is that electron affinity is less exo because your this fluorine has a very small atomic size. Hence, again, incoming electrons can experience repulsion from the valence electron shell or the quantum shell. Understand? So please take note of what's the abnormality. Okay, next one. What else? Another trend, Vivian? So again, electronegativity is another one. What happens to electronegativity as we go down? So electronegativity decrease. Is there any abnormality? No. Fluorine is the most electronegative. Understand? So take note about that. Next one. What else is another trend, Grace? Is your? What is it? Yes, melting point, boiling point, but we don't use this to explain, right? So that one is another one, right? So we learn melting point, boiling point of your this group 17 will actually increase or decrease. Increase. Explain. Standard answer. Why from chlorine? Fluorine, chlorine, bromine, iodine. Always increase. Electron size to form stronger ID, which is instantaneous dipole induced dipole, so more energy needed to overcome because they are non-polar molecules. This one is talking about from your this chlorine, okay, to your this bromine to your this iodine. What's the state of iodine at RTP, Grace? Liquid. Liquid. Solid state at RTP. This is liquid, this is gaseous, this is gaseous. Talk about astatine, solid. Understand? So take note about that. Okay, another physical trend that we need to take note of is bond energy or dissociation. So what happens to bond energy or dissociation? Vivian? So your bond energy is actually weaker and weaker. Is there any abnormalities? Have. Okay, the anomaly, please take note, is actually fluorine. Alright, the bond energy of fluorine is actually weaker than the bond energy of chlorine, even though fluorine has a shorter bond length. Reason, what do you write for exam? Vivian? Not about polarity, yeah? It's always about size. Because it has very small atomic size. So what happens to the electron in that covalent bond? Experience? Greater electronic repulsion. That's why you weaken the bond to a greater extent. This one is got to do with what? Also your this atomic size. This one is got to do with what? The atomic size as well. So please take note, when is it abnormal cell? Alright? So this here, got one more. What's the last physical trend for you to take note of here? Is color. Okay? Color actually darkens as you go down your this group 70. So these are your this basic physical trends I want you to take note with regards. And please know how to explain and please know which one is abnormalous. Alright? Next one we need to take note is your chemical properties. For your chemical properties, there are some things we need to take note what happens to the reaction when we compare with your chlorine, bromine and iodine. Okay? First one is, you are expected in syllabus to know well that for your first chemical reaction is the reaction with minus Fe2+. Alright? You are expected in syllabus to know if I compare chlorine, bromine, iodine. Only your this chlorine and bromine can react with iron 2+, alright, to become your this iron 3+. Because we already learned your this first electron affinity is less exothermic. So in other words, right, as you go down, oxidizing power actually is going to be decreasing. Remember, group 17 are oxidizing agents. The oxidizing power actually decrease. So, or your E naught value is becoming less and less positive. So that's why, right, again, you can see as here, when we undergo reaction, bromine and chlorine, okay, can react with iron and you will form iron 3+. What will be the observations for this, Grace? Color of this is what? Reddish brown is iron 3 hydroxide only, but iron 3 aqueous solution is what color? Brown or yellow. You understand? Make sure you know. So, but iodine can react or not? No, you can calculate your E naught cell. It's going to be a negative value. So that's why, right, this helps to distinguish, okay, your this Cl and Br from my this iodine. Because iodine cannot react. Okay? Second thing we need to take note, the reaction for your group 17 is that group 17 can react with my thiosulfate. You are expected in syllabus. How do they react with thiosulfate differently? Remember, oxidizing power decrease. So only your chlorine and bromine, when they react with thiosulfate, you can fully oxidize this thiosulfate to form sulfate ions. Because can you tell me, Vivian, what is the oxidation state of sulfur in thiosulfate? Calculate. Mental sum is what? You sure? Hello, it's S2O3 2 minus. Oxygen is always 2 minus. What is it? Plus 2 or plus, sorry, this one. Plus what? Plus or minus? You cannot just tell me 2.
Plus 4.
Huh? Then you divide by 2 or not?
Yeah.
So it's plus? Yes, plus 2 to become what? What is this oxidation state?
Plus 6.
Yeah. So do you see how it can oxidize from plus 2 here to become plus 6? Same with the bottom. But iodine, right? Do you have higher or lower oxidizing power, Vivian? Lower. So if I have iodine, notice how iodine is minus I2. When you react with thiosulfate, you realize instead of sulfate, it actually forms your S4O6. Sorry, forgot balance. So when I form this S4O6 2 minus, do you see the oxidation state? Great, so what's the oxidation state of sulfur here? Because I already know this is already plus 2. This is plus what? So you say this is 2 and what? 2.5, so it's again 2.5 or 2.5, okay, for your S. Do you see the extent at which sulfur is oxidized is lower? Not bad. Okay. Okay, so but can you use this to distinguish anything? No. But you're still expected to learn in syllabus the formula because you know sometimes they will like to react, especially iodine with your thiosulfate or bromine with your thiosulfate. Okay? Last one. Again, for your this one, we need to learn what is this reaction. That means displacement reaction. This is always the best reaction. Okay, to distinguish between all of your this chlorine, bromine, and iodine respectively. Because as you go down, first electron affinity is becoming less exothermic. E0 reduction, okay, or potential is actually going to be less exothermic. So that's why, again, the less reactive metal will be less likely to displace the more reactive metal from its salt. Or you can say the more reactive metal can displace the less reactive metal from its salt. Now besides this, what else must we also take note? You have this hydrogen halides. Three chemical trends that we need to take note for hydrogen halides. Let's go through. First one, Vivian, the first physical trend that we need to take note is got to do with thermal stability. What happens to thermal stability as you go down the hydrogen halides? So thermal stability actually decrease because why? What is the reason you used to explain? Do you talk about electronegativity? No, then you talk about what? Bond strength between hydrogen and halogen. The HX bond as you go down this group, isn't it longer and longer? So isn't it weaker bond? less energy needed to overcome. Second one is got to do with acidity or acid strength. What happens to acid strength, Grace? What is the reason you're right? Because you asked me, right? So it's what? Two. So more readily it's broken, okay, for dissociation of H+, alright, to actually be a stronger acid. I repeat, strength of acid is dependent on two things. Number one, your this bond strength between the hydrogen and whatever atom. So you can take note of the dissociation of H+. Second one is stability of the conjugate base. Okay, next one is oxidation. Ease of oxidation of your this hydrogen halides is what, Vivian? Is it easier to oxidize or more difficult to oxidize? Easier to oxidize. Okay, I repeat, ease of oxidation is easier, alright, because your this HBr or from your HCl to HBr to HI, right, require again is because it's very unstable. It can be most readily oxidized at even atmospheric oxygen. But your HCl needs to be oxidized by a strong oxidizing agent. Understand? Clear? Now, next one we need to take note of. Last one is the reaction of your this silver halides. Silver halides, one thing we need to take note of. Let me go and erase first, sorry. So again, for silver halides, one thing we need to focus on is this reaction with your excess aqueous ammonia. So can you tell me, Grace, before we go through, what happens to KSP of your this silver halides? What happens to the KSP? Because these are all salts, alright? Increase or decrease? I wanna ask you a very simple question now. You're this silver iodide, right? Agree? Is it soluble or insoluble in excess aqueous ammonia? Insoluble, right? If you're insoluble, do you think the IP can easily exceed the KSP? If you are insoluble, do you think IP is trying to insinuate IP always exceeds KSP, right? Okay, do you know where to form PBT? IP is? So if I always insoluble, that means the IP, right, regardless whatever change in IP, can always exceed KSP. Does that make sense? For your this silver iodide. Because it's always insoluble in excess aqueous ammonia, right? The logic you can think about this is IP always exceeding KSP to remain insoluble in ammonia. Yes, because you always form PPT, what? The PPT still remains, what? If you say the IP never exceed, that means the PPT should dissolve, right? Agree? But is IP always exceeding KSP? Yes, right? So do you think the KSP of your this silver iodide is high or low? High or low? Sorry? It's very low. But your this silver chloride, it is always going to dissolve, right? So do you think the KSP is high or low? High. Because the IP, any changes, right, sometimes can go below the KSP, then that's why dissolve, ma. The logic is this one, right? So what happens to KSP as you go down? The question is, you all must know how to explain. I'm going to erase, okay? I already explained what the things they like to test. This is very important because it's also part of your solubility, and you see countless of times they like to test on this. You need to learn how to explain, okay, in terms of equation, and write down the explanation wise. So we try the first one, which is silver chloride. Silver chloride, we learn from your salts, right? We need to come up with two equations why solubility increases as you add more aqueous ammonia, right? So, Vivian, as a salt, you're always tell me this arrow. Then for what? However, if I were to have excess aqueous ammonia, you are expected to learn what is the complex form. What will I instantaneously form? By the way, this is also part of your Tollens reagent. So, question is, when this actually forms, what happens to your Ag plus concentration? Decrease. By Le Chatelain's principle, POE will shift. Right. My next question is, your IP, okay, will actually first decrease when your Ag plus forms complex with minus ammonia, right? So that's why we know POE actually shifts right to increase your IP. However, what happens to this? Is it still soluble in excess aqueous ammonia? Yes, right? So you must tell me how the increase in IP, okay, does not, because we know it's not soluble, so it does not exceed, okay, the high KSP, despite the increase. So that's why you will then mention, okay, the salt will actually be soluble in excess aqueous ammonia. You understand? Okay? Make sense? Grace, you follow? You follow, right? You now tell me. Because if I change this up to Cl AgI minus, same concept, right? But we know that even with concentrated aqueous ammonia, okay, excess concentrated aqueous ammonia will cause your AgI to remain insoluble in excess, right? How are you going to explain? Because Birex should have this concept, what? So what must you mention this time? IP decrease, okay, when your Ag forms complex with your this ammonia, right? So POE will shift right to try to increase. But again, what can we now mention? Increase in IP this time will easily exceed the low KSP. Understand? And then that's why you will say that, okay, IP increase easily exceed the low KSP, that's why the AgI remains insoluble, even though by right PO issues, right? You understand? Because we already say KSP decreases. Make sense? Please know how to explain now, because this is important now. The last one you need to take note. So we have your chemical reaction with Fe2+, reaction with thiosulfate displacement reaction, hydrogen halide, silver halides. Last one you need to take note of is got to do with your electrolysis. Is how your this chlorine, okay, can react with sodium hydroxide during the electrolysis of brine. Vivian, you follow? Last week I mentioned before when I have here chlorine produced at your anode, okay, but because even though hydrogen is formed at your cathode, OH minus is formed as a byproduct, right? So that's why you also can form NaOH, right? So what happens if they mix together without the membrane? You form and okay, so please take note now. This can even occur in cold aqueous sodium hydroxide, let alone warm aqueous sodium hydroxide. You can further undergo more reaction. So in cold, okay, sorry, they're right here. In cold sodium hydroxide is like that. If I have to have warmer, do you agree more reaction can occur? So if it's warm, instead of forming ClO, okay, I will actually form NaClO3, okay, as well as your H2O. Clear? I forgot balance, let me balance 5. So this one is actually 3. Okay, and electrolysis is usually very warm. So take note about the things they like to test for group 2 and group 17, can study for it one. Because group 2 and group 17 question, I can tell you, is all pure textbook answers. Understand? So can cram and never lose marks for it. Right. Same concept. Are you done? Please do all the questions starting from question 1, 2, and 3. We are revising for group 2 and group 17 first. walk around to mark soon. I'm just concerned with the way you write. on the board for those who are fast enough. on about for part 1, 2, and 3. Let me know if I need to explain. I'll be walking around to see your answers. Now. You know why straight away know it's proton receptor? You look at what happens when this CHIL. This CHIL, right? You see this one has how many protons? No? One less, right? So it means that this one must have accepted a proton. That's why I know it's a proton receptor. You understand? Okay, where's the other one? HBI. Step, yes. How do you compare an ionic size? Effectiveness of orbital overlap, yes, but what you compare an ionic size? You haven't answered my question because they are covalent bonding. That's why I'm asking you why you compare an ionic, not atomic size. You understand? So again, you are using wrong terminology. I never say you are wrong. Okay? You never mentioned about that. Right? Effectiveness of orbital overlap increases. Okay? As energy needed to overcome. Yes. So this one is less stable. So I only can give you maximum 2 marks because of wrong terminology. Rate of reaction will increase. Code data. Energy needed required to By the way, Vivian, you have to write the keyword is part of the rate determining step. And I'm out? No. You know why? If I were to compare here, just compare, we don't know what happens to this. But when we look at this, do you see it's one less hydrogen? This the hydrogen goes to here. So this is acting as a proton acceptor. You understand? Never draw arrows here, never penalize. You have to write fast here for this one. No, I will not accept. It's the lone pair of electrons that is attracted. Because the electrons are the one with carrying the negative charge. Okay? So there's the penalized part. So, yes, this is the major product. Okay? You know why, right? This is a secondary or tertiary, right? So that's why it's the most stable. When you put here, it becomes a primary alkyl ion. Steric hindrance is lower. Okay? This is the explanation. Again, like I said, why are you comparing this? Should it be ionic size? Because you want to talk about the bond energy between H and X. So it's atomic size or ionic size? Atomic size, right? So you should be actually telling me the atomic size of Cl to Br to I increases. So either you use the effectiveness of orbital overlap, or you say how the bond length is longer. So your bond length is longer, bond strength is lower, which we never talked about here because you use ion. Ion, there's no bond length because ion is electrostatic force of attraction. You understand? So no, I cannot accept. You cannot say bond length of ions. Ionic bond no length one because they are not overlapping and sharing orbitals. You understand? Wrong terminology, yeah. Okay? If you change this to hydrogen and halogen atom, then fine. I accept. Okay? The other one you say is weakened, okay? And then less energy required to overcome covalent bonds, and thermal, don't know why suddenly can be covalent bonds when you already read ion. Miraculous, right?
Okay, so if I talk about the bond length, then is
Effectiveness of orbital overlap lah, so it's a covalent bond. That's why later you see the answer. So just to go through for part 4, they say how come it is going to be as such. First thing is that you know that halogen decomposes to form hydrogen gas and your halogens, right? So thermal stability, please take note, actually decreases as you go down from HCl to HBr to HI. Why? Keyword is size of the atom. Size of the atom increase, so that's why the bond length actually increase. Or if your school insists of writing that the effectiveness of orbital overlap between hydrogen and halogen atom is less effective or decreases, I also accept. So the idea is that it will become weaker. When it's becoming weaker, bond energy actually decreases, thermal stability decreases. Understand? So I repeat, instead of writing bond length increase, you also can replace with effectiveness of orbital overlap. Okay, actually increase. Okay? Grace, I haven't marked the other one. Bond energy. We put data. Bond energy never overcome. Reaction decreases. Okay. Okay. So you should know for the other one, your rate of reaction decrease. Same thing about your this bond energy of HX. HCl has stronger bond energy, and you have to quote the data from the data booklet. Okay, so rate of reaction is slow because more energy is needed to overcome the HCl bond compared with the HBr bond. I just want to point out, how come I know this Bronsted-Lowry base? Alright, it's because you compare with your this PH3P CH3 to become your PH3PCH2. There's one less hydrogen in the atom, means it's gained by that particular lithium compound. So that's why you know it's a proton acceptor, or you can write Bronsted-Lowry base. Okay, please take note everything in red for electrophilic addition is a must-have. If you are missing this, I will penalize. One thing I want to point out is that when you want to say that nucleophile bromide is attracted to the carbocation ion, it must be from the lone electron pair, not from the minus sign. Okay? Yeah? Okay, I'm going to write down the answers for question 2. You can try question 2 first. So walk around and see. Remember the standard answer. Again, can I mark first? Question 2. No. Hey, this one when you want to find mass of carbonates formed, it's never got to do with thermal stability. It's always got to do with number of moles. The mass of these two carbonates are the same. But you have this magnesium carbonate has what kind of MR? Higher or lower? Lower, right? If you have lower MR, would the number of moles be higher or lower? So the number of moles is going to be higher, like you divide by a smaller number, like if it's higher, right? So what happens to the final mass of magnesium carbonate? Magnesium carbonate will actually have a, hey wait, you're right, smaller, but your explanation is wrong. Okay? So,
How come it's not as like calcium chloride is not stable, so it's less likely to decompose to form?
but they ask you for the final mass of the carbonate octet. Even if you actually have the same the carbon dioxide that decompose, you tell yourself the mass of carbon dioxide formed, is it really because of thermal stability or the actual mass, or is it because of mole calculation? You always do mole calculation, you see. So that is the explanation why. Because you will see how the other one, they will never ask for questions that is repetitive answer. Am I right? If they give you 2 bullet points, it's for 2 different reasons, right? Okay, so less likely to decompose. CO to a lower extent. You understand? I'll give you 1 mark for the correct temperature and the correct final mass, but I cannot give you the other 2 marks for explanation. Okay? Grace, can I see? Temperature at which the mass is what? Lower. Is this what you call lower? I'll give you 1 mark for this. You said ionic radius increase, density, charge density decrease, polarizing power decrease, electron cloud less polarized, less weakened, thermal stability of this is greater. Fine. But you never tell me about why the final mass is lower. So I can give you 2 marks only. Like I already mentioned, whenever you want to mention mass, it's always compare moles. And how you compare moles? MR. Okay? So just to want to hear, don't want to hear is fine. So again, if you ever want to compare mass, right? Final mass of any compound is always based on number of moles. So notice how they start off with the same mass, but this one actually has a lower MR. So the number of moles are same mass divided by a lower MR. You should know the number of moles is actually larger. Okay, than that of calcium carbonate. That's why the final mass is always going to be low. Next one, temperature required is going to be lower. Okay, for magnesium carbonate because it has lower thermal stability. So you want to compare, you can compare Ca2 plus having a high, sorry, not C, my bad, Mg2 plus having a higher, okay, charge density, so polarizing power is higher. Do you realize it's the same template? And then you will say how Mg2 plus can distort this large anion, carbonate anion to a larger extent, weakening this to a larger extent. And that's why thermal stability decreases, lower temperature. Understand? Know the standard template. Question 2, part 2 is always standard template. Okay, I write down the trends for part 3, part B. By the way, what is X going to be, Vivian? For question 3A, Al2O3, reason why? It's amphoteric because the reactant can react with both sodium hydroxide and aqueous hydrochloric acid, and then they also say X has a charge of +3. How about your Y, Vivian? Grace? P4O10. Reason because they use the word +5. Cannot accept P4O6. Okay, I only can accept P4O10, and they said they only can react aqueous sodium hydroxide, means it's an acidic oxide. Just now I written down for your X, what is the half equation? I'm not going to go through. This one is basically what we went through for the periodicity. Anyway, I will be writing the answers on a board template for part B. Like I said, group 2, group 17 is all about template. Make sure you get them.
Wait, what if when the mole of MgCO3 plus is larger, then the final mass is smaller?
So again, when you have more moles, the likelihood to actually, because they are saying, right, the plots for your carbonate against temperature. So idea is, do you agree if I have more moles of magnesium carbonate to begin with, more can actually decompose to form carbon dioxide in that sense as well? Agree? So that's the idea. That's why more moles, that more can decompose, lower final mass. molecular size, strength of ID. Sure. Why you suggest here? Why? Hydrogen bonding is even stronger, right? Presence of stronger hydrogen bonding. Energy needed. Okay. Fine. What's this? Oh, okay. Ready? Unlock. Not Chris. Nope. Must even be higher than HR. You know why? Yeah. Okay, which is much stronger? I want to see higher. Next one. What's this? What do you know about orbital overlap? Does it matter? Strength of IDID is based on number of electrons or electron cloud size. It's not about effectiveness of orbital overlap. This here, irrelevant. Effectiveness of orbital overlap is got to do with strength of covalent bonds. But you're trying to overcome intermolecular force attraction. Does that make sense? Okay, so irrelevant here. Stronger IDID, so that's why more energy needed. Okay? Covalent bonds, correct. IDID is got to do with molecular size and your number of electrons. Okay? These are hydrogen bonds. Hydrogen bond require more energy to overcome than the weaker here. Okay, continue. Okay, question 4. Those who fast enough, you can actually again check your answer, but I want to walk around and mark as well for question 4. I'll be writing down the answer for 3C for those who want to verify. Remember, this will be a trigonal planar. You must see the 2 in front because there are 2 nitrates. Just to let you know, 2 double covalent bonds, 1 single covalent bond, 1 dative bond. I must see alternating as well. That means the 1 electron that is gained must always be gained by oxygen, not nitrogen, remember? If you want to gain an electron for an anion, must always be from the more electronegative atom, which is oxygen in this case. guys should know this already, as I can already mention, sometimes they will compare with other metals and you should know. What's the ionic radius of zinc? Can you tell me, Grace?
0.074.
Nanometer, 0.074 nanometer, and we get this from the data booklet, so it's actually much smaller than your barium. Can you tell me, Grace, which one has a higher charge density?
Zinc.
So if you have higher charge density, same thing, you must tell me why. So polarizing power of zinc is definitely greater, able to distort the anion, which is nitrate, to a larger extent. So you should know by now that zinc nitrate should actually have a lower thermal stability, decomposition temperature therefore lower. So it's the standard answer. Okay? So by the way, can I quickly go through? Vivian, can you tell me C part 3, what will be the equation with state symbol? You can write half in your equation for chem. Okay? I'll walk around and see your part 4 soon. decompose, right? And then the 20 sample, which is actually a mixture. How will you know that all this gas comes from solely from the trend? As you right now, right, O2 and mass of this is 8.7 minus x. Why do you use that? Shouldn't you just use the mass of your zinc and your barium? It means and then from there you do your calculation. Because right, they already say the remaining solid, white solid remain, a brown gas and whatever we like. So in other words, you need to find out what is your this white solid because the white solid remain, it should be actually your this barium decomposed at here. Sample heated to 350 when barium nitrate decomposed. So it means that this decomposition of this white solid remaining behind is just purely zinc oxide, right? That means 11.3 U minus X. Because this 11.3 right, is, we know that if it decomposes at 300 and 350, all the zinc nitrate, is it there? Or not there? So we are left with zinc oxide, right? Agree? So in other words, sorry I wrote wrongly, barium, should use barium and zinc instead. So if I use barium, right, zinc is this, right? Then we know the barium will not decompose, right? So this 11.3 minus the X is your zinc oxide, right? Does that make sense? 11.3 minus X is actually your zinc oxide. So from there, right, can we therefore find out what is the number of moles of my zinc nitrate from there? Should be using this because you use 8.7 minus X, very wonky here. Are you saying that, but some of the barium did not even decompose at all, right? So it's already for you to use this. You understand? Okay, so find out what is the number of moles of my zinc nitrate first. So I will explain clearer here. Because we have a mixture, this is for question. Let's see part 4. Since we have a mixture of 2, alright, so in other words, we need to let, okay, your barium nitrate mass be X first. So as such, my zinc nitrate mass will be the 20 grams minus my X here. They already mentioned you are heated to 350 degrees Celsius, so the barium nitrate would never ever decompose, but the zinc nitrate will decompose to zinc oxide. So it means that the mass of my zinc oxide should be what? Since they start off with, they end off with 11.3, right? 11.3 minus whatever barium nitrate that did not get decomposed, which is also the white solid form. Alright? So do you agree the number of moles of zinc oxide should be equal to the number of moles of zinc nitrate, because its ratio is 1:1. Okay? So I know is, by right, 11.3 minus X is the mass of my zinc oxide divided by my MR, which is 65.4. Alright, and my 16. Do the same for here. Zinc nitrate is 20 minus X divided by my MR, which is 65.4, 14, and 16. The number of moles should be the same. Solve for X. So Ray, solve for X for me. Tell me what's your X. From there, you should be able to calculate what is the mass of my zinc nitrate. And then you can find what is the percentage by mass. Understand, Grace? I can make them the same because if you write down the balance equation, the mole ratio of zinc nitrate and zinc oxide is always the same. 1:1. Barium nitrate did not get goes, how will you know how much is left? You don't know. No. So if you use this working, at least you can solve. I need to go through another 2 minutes time because I still got transition metals. Please at least tell me what's your value. The rest of it, I already given you the answer. So Grace, waiting for you to tell me what is your X.
For enthalpy,
Hmm?
the sign doesn't matter, right?
Chef.
As in like when you're comparing values, like the magnitude.
You just tell me again. No, you still need to tell me enthalpy of hydration. Is it more or less exothermic? You cannot just tell me the sign and magnitude.
So I cannot say it decreases.
Please never ever write decreases. I've said already. Always write more or less exo or more or less endo. Grace, whenever you're ready, shout out your answer for X. Four 4.7427. What is your mass of zinc nitrate?
$15.278.
15.278, yes. So again, you should be able to get this 3S. Okay. Just showing you the steps. Huh? Ready? Okay, I want to do transition metals. So I already given out the answers for question 4, so you can actually use this as your starting material. Let's go through transition. Transition metals, again, I want to talk about what kind of questions they like to test. It's quite generic one now. So again, typical things for transition metals, they always like to test for these physical trends that they have in common. That means things that are always in common. Number 1, you must know they have actually very similar, few properties that are similar. First property that is always similar is what, Vivian? Transition metals always have similar atomic size or radius, okay? They also have very similar, again, ionization energies. When I talk about ionization energies, I'm focused on the first and second. So let's learn how to actually explain. For atomic size and your this first and second ionization energy, the explanation is always very similar, right? First thing, what must we always mention, Vivian? Because we know for transition metals, example, I have manganese. Manganese, the noble gas configuration is what, Grace? Then later we'll try for iron. Noble gas configuration is what, Vivian?
3, 5, 4, S2.
And then here iron, 3d4 4s2. Do you see how we always fill out your 4s first? Because 4s usually is of a lower, okay, energy level than 3d. Okay, so what's the first explanation, Vivian? How come it's always the same? Because whenever we add electrons, do you see from here to here, we are always adding to the inner 3D quantum shell, right? Agree? So the last quantum shell, isn't it always 4s? So what does this mean? Do you agree? If you have increasing number of 3D, what does it actually do? You will effectively shield what? Never mind. We know it's based on this formula, right? But how are we going to explain how come your atomic size and your first and second ionization energy is always similar? Standard answer you always write is that as you go across the period for the same group, that means transition metals, okay? Electrons are added to inner 3D, okay, shells, right? If I add to the inner 3D orbitals, what does this mean? Your outermost is still 4s, right? But do you agree you have more and more inner electrons to shear away your outer 4s? What happens to your screening effect? Increase, right? Agree? And this screening effect will increase such that it will cause your this ENC to this time remain almost constant, because this is also increasing. The idea is that they are increasing to roughly about the same extent. You understand? That's why ENC is constant. So you must say how your this inner 3D, okay, electrons can effectively shield away outer 4s such that ENC remains almost constant.
Explain the second point.
Do you see from here to here, you have more and more 3D electrons? So will I have more and more electrons to shear away the outer 4s? Because this will start to increase, what? Right? Agree? Remember, screening effect is not just by increasing number of quantum shell. Your increasing number of electron shells, okay, or increasing number of inner electrons can also increase screening effect. You understand? So idea is that you can effectively shield outer 4s, the ENC remains almost constant, electron cloud size can remain almost constant, or for your first and second, you also say how it will actually cancel out the increase in screening effect, nuclear charge. That's why your first and second ionization energy is also almost constant. Because you see, I'm always removed from the fourth. Okay, quantum shell. Okay? Clear? Why? It means repel. Shield is almost repel. Screening and shield are almost the same as repel. That's why if you have more inner, will you repel to a greater extent? Because this is where your 3D is, what? Your 4s regardless is still here, what? You have more and more, wouldn't it also repel this to a greater extent? That's why you can say effectively shear away, such that it will cancel out the increase in nuclear charge. Yes, nuclear charge is given by your dependent on number of proton number. So number of protons will definitely increase, right? But they are saying that the number of inner electrons also increase. So they will cancel out each other. That's why this one almost constant. Make sense? Okay? So this is what they explain, huh? Please know. So the physical trends, I want you to take note about this. Melting boiling point, please take note. They also, again, same property, they are very high. Melting boiling point density is also very high. But I want to go through the second thing they like to test is your this unique chemical properties for your transition metals. First property for transition metals, you must know how to explain why they have variable oxidation states. Standard answer to explain why variable oxidation states is what, Vivian? Always say how?
The energy of the 3D
is of close
close
similarity. Understand? So you can say how your this close similarity in 3D and 4s electrons. So energy level of 3D and 4s electrons are of close similarity. Okay, so that's why once we remove the 4s, not much energy is needed to remove the inner 3D electrons. That is what you write, right? But we know one unique abnormality is zinc. The anomaly we learned is zinc. Zinc only has, okay, a +2 oxidation state. But the question is why? Grace, why? So what does that mean? Why fully filled 3D orbital? I thought the energy level is close similarity. What did I say as you go from your zinc onwards? Nuclear charge becomes very significant, right? So from zinc onwards, nuclear charge becomes very significant. Why? Such that the nuclear charge becomes so high, they no longer have close similarity from zinc onwards, because they will pull down the energy level from 3D, okay, such that it becomes even lower than 4s. You understand? So that's why not a lot energy is needed to remove the inner 3D. So how do you explain? It's because nuclear charge is significantly stronger. So again, energy level of 3D becomes lower than that of 4s. Okay, a lot of energy is needed to remove the inner 3D electrons this time. Okay, clear? Okay, next one. We know that besides variable oxidation states, we need to learn about ligand complex. For ligand complexes, few things we need to focus on. First thing to explain is the definition of ligands. Okay, you should know ligands. What's the definition? Because they cannot. Are they neutral or are they anions? Can be both. Okay, then either be a neutral molecule or an anion, but must contain what? At least one lone pair of electrons to donate to a low-lying vacant d orbital of the metal ion or the metal atom in order to form a dative bonding. So I repeat, it can be either a neutral. So example of this are like what? Example of ligands, okay? You need to know is like my ammonia, okay, or even chloride. But these are all monodentate ligands, means they only can form maximum one dative bond per ligand. We know there's such thing as bidentate ligands, right? The word bi means two, right? Means they can form maximum 2 covalent dative bonds per ligand. Alright? So please know what's the definition. Second thing they like to ask is the coordination number as well as the shape. You are expected in syllabus to know the coordination number of 2, 4, and 6 shape respectively. 2 is usually linear. 4 again is your this tetrahedral or square planar, wherever they mention. 6 is octahedral. I said before, your shape, okay, or what is coordination number is the number of ligands surrounding the metal atom. That's why if I have Ag, simple ones that you're expected to learn in syllabus, ligand complex, this is coordination number 2, also known as Toland's reagent. I also can have your AlOH4. This is coordination number 4. So things like this, you are expected in syllabus to know certain ligands. Water you should know already is always H2O6. So coordination number is 6. Okay? So these are some of your this ligand complex. Now, Again, why must we take note of ligand complex? Because the type of ligand we have can affect color. Okay, usually the stronger the ligand, it can repel your d orbitals, okay, to a greater extent. Alright, and we also need to learn this thing called ligand exchange reaction. Ligand exchange is when a more reactive ligand, a stronger ligand, my bad, is able to displace, this weaker ligand from its complex. So in order, right, you are expected in syllabus to know, it always stands from your CN, okay, followed by this ammonia, and then we have this OH minus, and then H2O, and then this Cl minus, Br minus, I minus. Okay, from strongest to weakest. Alright? Okay, now, anyway, that's why you learn, right, got copper. You all recall? Copper with the ammonia complex. Oops, sorry, it's a square bracket. Compared with copper with the weaker ligand H2O. This here is actually light blue in color. But do you see if I have stronger ligand, it's actually deep blue solution that we learn under QA. So that's why. So we need to take note, ligand exchange. Usually stronger ligand able to displace. This is related to color. So the third thing we always like to talk about is actually your color. Alright, let's go through as a recap. First thing we need to take note, what can form colored compounds? There's few conditions to form colored compounds. Let's focus on the conditions first. Condition number 1, in order to form colored compounds, especially for transition metals, what's the first criteria we always must have about the metal? Ion, not metal, metal ion. What is it, Grace? So the metal ion, not metal atom, must have, partially filled 3d orbitals. When I say partially filled, your scandium don't even have partially filled because scandium will always just form this 2 plus, right? So 2 plus scandium is what, Vivian? Same with zinc, that's why they are never considered transition metal. Zinc, you hopefully know, is just simply my 3d10. Because when I lose your 2 electrons from the 4s, it's just fully filled, right? It's not partially filled. That's why this is not a transition metal, right? How about scandium? Oh, scandium is sorry, plus 3, my bad. 3 plus. So it's what? Just AR, right? They don't even have 3D. By right, no need to draw this out, but I try to show you they don't even have 3D electrons. So the ion must have partially filled 3D. Right? Why? Because you need this partially filled, so for DD transition to occur. Do you know what is DD transition? Usually electrons, right? That means your dx, y, dx, z, y, z, dx square minus y square, d again z square. They are at first degenerate, right? Degenerate means what, Grace? They have the same energy level. But we know ligands, all this, right? Hopefully, you are expected in syllabus to know how to draw the orbitals. If I just draw this, any one of these 3, this one first, whenever we draw x, y, z. So what must this be? The lobes are in between or along the axis? In between. So because it's y and z, is in between y and z axis. Understand? So hopefully you know if x squared y squared, if I draw it in blue, for x squared y squared, it will be again along the axis. Something like that. Okay? So second criteria is the nature of ligands. So this ligand, so the idea is nature of ligands is 1. The stronger the ligand, the darker the intensity of color change because you have greater repulsive effect. What do I mean? Ligands, right, when they approach any of this orbital, so let's say I have this ammonia ligand, approach the orbital. When they approach the orbital, they always approach along the axis. They will never approach in between the axis. So when they approach along the axis, do you see how, again, which one will repel to a greater extent? These two, right? Agree? Because they are the only ones located along the axis, and then when they repel, they no longer become degenerate. They will actually have a higher energy level. So do you see there's an energy gap within them? But if you have a stronger ligand, because you have 2 types of ligand, right? Imagine if I have water molecules and I have ammonia. The stronger ligand will actually form a greater repulsive effect such that you have higher energy level. This one shift higher. Okay? So wouldn't they later be able to absorb more energy from the electromagnetic spectrum of the visible light? So that's why the color intensity is going to increase. This is the idea. Second one is nature of this metal ion. Idea is that a metal ion can have different oxidation state. Different oxidation state may give different color because you have different extent of repulsion again. More electrons, more repulsive effect. Less electrons, less repulsive effect. That's why do you see your iron 3 plus versus iron 2 plus? Iron 3 plus, right, again, you will have reddish brown or yellow, but your iron 2 plus is green, right? So that's fine. Okay? But let's go through the standard answer. There is always a standard template, right? Agree? To explain why certain, let's say iron 2 plus got color or why the zinc has no color. So let's go through standard answer. You will start off with, for example, I want you to compare why iron 2, okay, chloride has color, but zinc chloride is colorless in solution of white color. So this is what color, Grace? By the way, you're expected to know the color, so let's go through as a recap. All soluble salts of iron is always green. This is white, right? Now, ready? Tell me what's the color for V3 plus. And then I have V2 plus. And then last week I went through the VO2 plus. And then we also had the VO2 plus here. Is there more? No more. Okay, so what's the color of this, Vivian? Sorry? So, huh? This here is blue in color. Understand? Alright. This here is actually what in color? We went through this last week. Remind her? Yellow. This is what in color? Vivian? B3 plus. Green. And then finally? Okay, clear? We also expected to know your CR3 plus. What color is CR3 plus? This is your dichromic. Turn the other color, the CR3 plus. Green. Then the CR2072 minus is what? Orange. How about we have your this MN2 plus? Pink. And then your MnO2 brown. And then we have MnO4 minus purple. Please know all this color. Okay? Okay, but anyway, let's go through the standard answer for your this color. So first one, what can we mention? Can you tell me? Grace, standard answer, why FeCl2 has green color? What's the standard answer? Because, first one? energy levels with n energy between them. So the d electrons, so the electrons one here will absorb in a beacon, right? Agree? So when they promoted to a higher energy level, so what does this mean? How we visualize color? Wavelengths will be, therefore appear as? Yes. So I'm going to explain because what is the standard template to explain why this one has again color, right? So first one, you always must tell me keyword in presence of ligands, right? So always tell me in presence of ligands, okay? Same thing. You will say how your this Fe2 plus, okay? D orbitals are split into two groups of different energy levels, or you can split into two different energy levels with an energy gap between them. Okay. Second key phrase you always mention is a d electron will be promoted to a higher energy level, or promoted into a higher energy vacant orbital. All right, and then during DD transition is the keyword. Then after that, third bullet point, you always say the D electron absorbs wavelength of light from the visible spectrum, and light energy not absorbed is complement to the wavelength of light absorbed, appearing as green. Agree? I repeat, either you say the light energy not absorbed will appear as the color of the transition metal complex. Alright, I will also give you the credit. Clear? How am I going to explain why zinc has no color? Vivian. Zinc 2 plus or zinc? Please specify, because I already said it's always based on metal ion. So zinc 2 plus has? So what cannot occur? DD transition, which is this. DD transition, whereby electron promoted from a lower energy level to a higher energy level, is impossible. Understand? So take note. Still must mention this, that DD transition is not able to occur. Clear? Next one. Catalyst. Question, cellular test for catalyst. Two types. There's actually three, sorry. So let's talk about your catalyst for heterogeneous catalyst first. So heterogeneous catalyst is one. Idea is how I recognize a heterogeneous catalyst is when your state is of different state to your this other reactants. Example, nickel in hydrogenation of alkenes, iron in my Haber process. Okay? But we learned there's always key phrase, right? Agree? So if they have a different physical state, how do they actually function? Come, let's hear. Grace. There's always 3 standard answers, and I said never ever lose marks because transition metals can just memorize, right? The template. What's the first template we always write? Is that we always mention how? Okay, specify in exam. Will, keyword, adsorb with a D, not B. Okay, adsorb onto? Yes, which is the active sites of the catalyst. So keyword, adsorb to the active sites of catalyst surface by forming what? Weak attractive forces. Next one, Vivian, how do you actually mention standard answers? Weakening? So, because when they are brought closer together, you're weakening your this whatever bonds. Specify the bonds. If it's CO, CO, OH, OH, okay? And then not only that, and not only brought closer together to weaken the bonds, but also orientated in the right positions for reaction. And then finally, how do you actually mention, Grace? So what happens after this? I'm missing one key phrase, which is what? All this will help to? Yes. And then when reaction is complete, what must we mention? Is it reactants? Because reaction is complete, no more reactants already. So products, keyword is dissolve and diffuses. So they dissolve and diffuse away from catalyst. Why must you mention about this? It's because you are going to say the active site are now exposed for other reaction. Okay? Exposing active sites. What I'm writing up is if they ever ask you, this is literally giveaway. Can study for. So don't ever lose marks for this. Okay? So this is your heterogeneous catalyst. How does heterogeneous catalyst function? Idea is because we actually can have close similarity in 3d and 4s electron, right? So that's why we can actually lose and gain electrons readily. Okay, so the reason how they function, underlying reason is close similarity in 3d and 4s electrons shells. Okay. How about homogeneous catalyst? Example is your iron 2 plus that we did last week, right? Agreed? Iron 2 plus with other reactions that are actually sometimes anions, still they tend to repel. By having a cation with the same state symbol, okay, can be functioned as a homogeneous catalyst. So how does homogeneous catalyst usually work? Like for this, we know it's close similarity, so we can lose and gain electrons. Homogeneous catalyst work is because they can exist stably in variable oxidation states. That's why I gave you, right? Please know E naught cell is relevant here. So sometimes they can have your this Fe3 plus can react with your iodide, form back, but as a catalyst it must be regenerated. The Fe2 plus form can further react with your this S2O82 minus. So you allow these two anions, which usually by default will repel from each other, but you allow reaction to occur. Understand? The other one is autocatalyst. What is the idea for autocatalyst, Vivian? Product is the catalyst itself. So the product itself is actually the catalyst. So if you have more products formed, again, faster and faster rate of reaction, the curve is usually a sigmoid curve. Understand? Clear? Okay, same thing. Pass down. We will do question again 1 and 3. Any questions I never get to do, I'll give you the answer so you can use this as studying. What I'm trying to say that all these are just memory work for template work. These are the type of questions that can best suit for exam. So know them well. Copper reaction?
Yeah, like the copper with the
Oh, you mean the QA? You're talking about ligands, right?
Yeah.
And complexes, right? You are expected to know how to explain housing, hydroxide, aluminium hydroxide, lead-2 hydroxide, soluble in excess NaOH. You also need to know your copper, okay, hydroxide. Why is it soluble in excess ammonia? So example, since you're asking for copper hydroxide, isn't it the same as what I went through? As a salt, it will ionize to form this two. But, however, we know that if I have excess ammonia, the copper 2 plus, they readily form a complex NH3. How many? 4. Okay? So what happened to this? Decrease in concentration PO shift, right? That's why it's becoming more and more soluble. Are you talking about this? Okay? You also need to know how to explain this what? This is under the salts what? The same thing, ZnOH. You're at 4, 2, 3, 2. Okay, ZnOH2, sparingly soluble salt. Same thing, in excess. Okay, sodium hydroxide. You can form a complex, ZnOH4. Okay, so do you see how this will also cause solubility to increase? Last one is your this. I'm not going to explain the silver halide, you should know already. Okay, last one is your this PbCl2 soluble in excess HCl. So idea is PbCl2 is sparingly soluble, form 2 plus and Cl minus, but in excess you will actually form the complex PbCl4 2 minus. Same thing, solubility decrease here. Okay. Alright. Anyway, I think we only have time to do question 1, so at least try question 1 now. Any questions, and whenever I go through, I will give out the answers. Yeah, go ahead.
Can you help me see like which topics I need to like revise on? Because my school is still really very
Mark yourself.
Because they do some practice, then they use the RIA.
It asks you to sketch the rates of the forward and the backward. Why you draw energy profile diagram? They say rates forward, so is y-axis is rate. X-axis is your this time. I draw here. Okay, because this is for a equilibrium, right? System initially at equilibrium, temperature increase sharply. So this is rate against time. So explain how increase in temperature affects the equilibrium of SO2. Did they say it's what? Exothermic. Oh, okay. So this is actually for reaction is exothermic. So if I increase temperature, that means the rate of the forward will drop, right? Agree? So at first they all start out here, right? So your rate of forward will happen after a while. It will actually, because we know rate of forward will drop, right? So rate of forward, the idea is that they will, I'll just draw here. So your rate of forward will actually drop, your rate of backward will actually increase, but eventually they will reach another new equilibrium. So this is when a new equilibrium is re-established. So this is rate of forward, this is rate of backward. This is what they want. Rate against time. Hey, tell us. Rough. Volume and gas, negligible? No, must be elaborate, yeah. We need to revise on solubility. Acid bases is also another. Calculation number. Explanation wise you're okay, but it's just calculation right now for you, and organic chem what is happening here. So they ask you, right, for your this P, you're going to form here to eventually this. In other words, you want to have an OH and a COOH. There is only one way where I can have OH and COH, nucleophilic addition, from your this ketone, remember? So I'm gonna, first thing what I can do is, I can become a ketone, right? So I become a ketone already. I become this ketone undergo condensation. This ketone when undergo condensation, you will have OH and then UCN. And after that, you undergo acid hydrolysis. Ta-da! So you need to revise on your mechanisms. I already say already, one thing you can do to revise for this is, you know you are a lot of reading paper now, right? You know your paper 3, sometimes you can just choose, right? Just choose all the questions that have all this kind of thing, then you go and do, spam. Just like how I say choose all the questions and have elucidation and do all the elucidation. So this is one thing you can do. Okay? All the prelim, just spam. Then at least, right, you become more and more familiar. Okay? QA. That's our elucidation. I already just say, don't present like this already. What did I say? Present like. Then at least it gives yourself clarity. Understand? And then usually, right, there should be more. Okay, I think it's because you couldn't find your other ones. So they gave you maximum mark for the explanation. So your 3 marks is for your compounds. I feel right now you need to go and revise on your acid basis solubility. And then your organic chem. Oi, this is pure memory work.
I thought I got right properly, but this is wrong.
Again, hello. I never teach you to write this. Okay? So first one you never tell me is that the ligand must approach. Which I just now mentioned, right? Ligand approach and it cause, again, the degenerate d orbitals to split into 2 different energy levels, or energy level with a gap in between them. You understand? Then after that, what must you also mention? You must say how electrons promoted a higher energy level, then you will what? Absorb what? Agree? Absorb light. You promote first during keyword you're missing is DD transition, and then you will say absorb wavelength of light from the visible spectrum. Cannot, no, because DD transition is when you promote electrons. You haven't even tell me that again a ligand will cause again your this repulsion. Okay, so keyword, right, you always must write first. Light when in presence of ligand. Okay, the electrons again, the d orbitals are split into 2 energy levels first. You must tell me how the energy levels are split first, then your electrons can be promoted from a lower energy to a higher energy one. Must split energy level first.
The DD transition is when the electron.
Correct. That's why I say when electrons are promoted during DD transition. Do you see the template? If you just follow the template, you should get right already. You understand? And then another mark is that why you never give you never talk about zinc. Where?
Yeah, it's the only one.
Okay. Okay, but anyway. This one is before or after the electrolysis. So now you know, I feel like I said,
Oh, that one.
I told you already, right? Okay, so like I said already, for me I think it's acid basis solubility and your organic chem. Organic chem is supposed to be your saving grace, not your downfall. You let me know if you don't understand, because when you were doing your this electrolysis, it looks fine. Okay? So that's the 3 you can try to focus on. But again, try to not just study on this one, but you just film them in higher priority. Okay? So for you, it's the way you write for some of them. Like those that I say can remember, you just memorize the template, please. The group 2, group 17, your periodicity, your this transition metals. And all this got template. Don't lose marks for template there. Okay. The other one thing I want to point out is you always have to draw the lone pair of electrons for me. If not, I cannot give you the full mark. Understand? In presence of ligands, degenerate d orbitals split into two energy levels. Okay, you have an energy gap. DD transition occurs, electron is promoted from lower to higher energy level, absorbing light. Okay, fine, I accept. Okay? Wait, I want to see your part too. Already say group 2, group 17, periodicity, transition metals. The answers are usually based on a template. Know the template well. Okay? You know what? Whenever you do a paper, you know what I always say? Keep moving forward. Okay? Don't ask me to say I think that, I think this. I can't change. I'm not Tom Cruise. Unless I can just go in Mission Impossible, help you change your answer, then it makes sense. But I already say keep moving forward. Okay? Focus on the next paper. Your next paper is bioprep. So focus on that. Okay? Please, I gave you one whole chunk of these bio things to actually take note of. And I also gave you a bioprep notes, right? So you're going to study from there. There's some things that you can prepare and memorize for bioprep, right? So go and memorize for that. I told you already, it's like sources of error, these variables. But usually we write ligand exchange because displacement usually is like irreversible, but ligand exchange, right, can be reversible. Like carbon monoxide is actually a stronger ligand compared to oxygen to hemoglobin, alright? But we can reverse the effects of ligand exchange by having high concentrations of the weaker ligand. You can also reverse and undergo the backward because it's all based on equilibrium. Understand? Ligand exchange is an equilibrium reaction. Where is my tissue paper? If you're fast, you can try question 3. Sorry, I mean question 4, part 1, 2, and 3. Again, Grace, when I want to see this, I always must see lone pair of electrons. If not, you are penalized. Understand? Plus 2. What is this plus 2? Your CU is here leh. CU is more than just a CL leh. Yeah. Kosong. No lone pair, no marks, so better draw lone pair. choose a question, please choose always the one that you're more confident in.
You know they ask us.
You do 4.
Actually no, I haven't.
Oh, but they ask you to do 4.
No. It's cause
I'm just telling you, based on this, I always been seeing your paper. Every time this one is the one that makes so low marks. So your choice of question is usually poor. Can you choose some questions that you're more confident in? You know, every time they ask you flip paper, ask you to check, oh, the paper number correct or not. You go and look at the whether the question you which one you're more confident in. What use that time to prioritize what? Right? Agree? You mean you're really so quiet go and count the number of questions and whether correct?
It's like when I flip they look the same.
They look
small.
Okay, so here straight away transition metal. You know already straight away transition metal is quite standardized already. Look at the topic, not look at the question. And then here, right, this is about ligand exchange because you see things like ligand and colored and why different color. That means you just need to explain the extent of repulsion. We already tell you this whole thing is based on this transition metal. Is this based on transition metal? Hello, you tell me. What do you mean all question onwards? So you look at the topic that you're more confident in. You don't tell me all words. Hello. So you will see which one you're more confident in. Like for me, it's like usually different students have different confident level of that. For me, I prefer to do all this kind of calculation. Okay. For you, you want to write more confidently. Sure, then you can do the transition method because some students feel like okay, I just textbook vomit out the template, then it's okay. Choose the topic. Okay, don't be so quiet. Your choice of your questions is usually very poor. So you please choose something that you can help yourself, not bring your downfall. Ligand exchange, correct. You say this place is also fine. This stronger ligand, this place weaker ligand, violet to bridge, sure. And then few drops. Where is the stronger ligand? Then F minus able to display the weaker C and sure, 2 turn colors. Then that's all. Okay? That's all.
Wait, like who asked me to write this one?
Okay, I will accept for this one when you say bound to the ligands, okay, then you will actually cause the splitting in the energy levels, okay? But this one, to be honest, the split in energy levels will occur before formation of complex. Because the moment the ligand approaches along the same axis, you will actually have splitting of orbitals already. Understand? But I will accept for this. Energy gap, then what?
It's like something like that.
DD, I don't care about this. The idea is the keyword is what? After you say this, right, then again, you don't tell me light is absorbed. Okay? You say first, hey, can you write in sequential order? The 3D electrons will be promoted to a higher energy level from a higher energy to from a lower energy to a higher energy level, okay, during keyword what you're missing? During DD transition, you can study that. During DD transition, and then what will this cause? This will actually cause, again, light to be absorbed from the visible spectrum, which is energy cap. Then you will write light is absorbed, okay, from this visible spectrum. Whatever light that is not absorbed, what is this? Color is complementary to the sure, which is in this case is the colored one. Okay, then you will say the colored form will be complementary to the color that is absorbed. You understand? Okay, always write in this kind of sequential order. Then you will not get wrong. Your way of writing is a lot of zang. That's why your knowledge and understanding for what is DD transition, what is again, all this is very wonky. Okay, here. Okay, do question 4 for this part. Yeah, maybe I will do question 4 part 2. By the way, draw for me the orbitals. 2 of them. Okay. Anyway, because of time, I have to end off here today. Let me pass you the answers. Wait, can I pass you? Yeah. Let me pass you the answers for this 2. Go back, go and revise. Alright. I already say already. Group 2, Group 17, transition metals. The answer, the standard, the key phrase is all very standardized, right? Nothing special. Understand? Follow the template. Alright? So you follow the template that I mentioned in class, right? You will always get full marks, right? Especially for your this color as well as catalyst, especially for the how heterogeneous catalysts actually work. Okay, with that, I end up here today.